Today, I'm John Paulo Boas, and I will be discussing thermal properties. So first of all, what is thermal properties? It is basically the response of a material to the application of heat. So heat capacity, the ability of a material to absorb heat. In this equation, you can see that C is heat capacity, and that's our unit joules per mole of Kelvin. Then the Q here is the energy input with the unit joules per mole. And P or dT is the temperature change. It is in Kelvin. There are two ways to measure heat capacity. Number one is heat capacity at constant pressure, or CP. Number two is heat capacity at constant volume, or CV. So most of the time, CP is always larger than vibrational heat capacity. We all know that atoms is solid materials that are constantly vibrating. They are constantly vibrating at very high frequency and vibrations of the adjacent atom. They are actually coupled by virtue of the atomic bonding. So as you can see here from the figure, here it shows many small balls. So what does it represent? The blue balls represent the position of the atom displaced due to vibration, and the orange color is the position of the normal lattice position of the atom. So due to this vibration, the atom is displaced or at the location localized upon location of the vibration. They happen in wave that travel let these waves are produced. Now the whole thing is so traveling lets this wave from whole thing. The dislocation we call it is elastic wave, or we can also call it sound wave. So these waves they have short wavelength and very high frequency. So the vibrational thermal energy for any material actually consists of a series of these elastic waves or range of distribution. And the frequency and only certain energy value are allowed, and the energy is to be quantized in a single quantum of vibration energy called quantum. So these elastic waves they actually participate in the transport of energy during thermal conduction. We call as temperature dependence of heat capacity. Thermal expansion. So what is it? Usually, solid materials they will expand upon heating and they will contract upon cooling so that it is common. As you can see, the initial length and this is the final length of this bar after thermal expansion. So change in length with temperature for solid material can be expressed using this formula. And the alpha L is we call linear coefficient of thermal expansion. And the unit is reciprocal of the temperature. It is a property that indicates the extent to which a material expands upon heat. The expand upon a certain heat treatment. So this formula is simplified to this. So, so this is just a comparison of a coefficient and thermal expansion among ceramic metals and polymers. And above all, polymers have larger thermal expansion coefficients because of their weak secondary bond. Because their bond is weak, so they have larger thermal expansion. So many, when they are applied in by heat increment, they will expand even more compared to metals and ceramics. Next, we have thermal conductivity. We can define this as the ability of a material to transport heat from high to low temperature regions of a material. itself. And the property that actually characterizes this thermal conduction is what we call thermal conductivity. So this thermal conductivity, it is a property that characterizes the thermal conduction process. So this thermal conductivity is, it can be defined as in this term of this expression. The Q is equal to negative K dt over dx, also known as Wheeler's law. So Q here actually is the heat flux for the heat flow. You can call it also the heat flow per unit time per unit area. In this area is taken at the perpendicular to the flow direction. So K is the thermal conductivity and dT over dx is the temperature through the conducting medium. So the units of K, Q and K are these. The minus sign indicates that the direction of the heat flow is from hot to cold or down the temperature gradient. And this is the comparison of thermal conductivity. According to the old materials, metals have the highest conductivity compared to ceramics and polymers. Polymers have the lowest thermal conductivity. So the energy transfer mechanism in metals is through atomic vibration. The motion of free electrons and in semi the mechanism of energy transfer in thermal conduction is just atomic vibration. Then for polymers, it is vibration and rotation of chain molecules. So the higher the thermal conductivity, it can transport heat from high to low temperature regions of a substance higher compared to ceramic or polymer. So next, I'm going to talk about thermal stress. So thermal stress, they are stress induced in a body as a result of change in temperature. So materials also experience stress, not only humans, but as well as materials. So materials tendency, how do they experience the stress? The expanding or contract, either expand or contract. So if heated was restrained to its original shape, Thomas stress will develop in the material so that stress in a material can be calculated using this formula. Engineering stress is equal to what is modulus of electricity and the Young's modulus of alpha L. Alpha L is the linear coefficient of thermal expansion in delta T. This is just the change in temperature. So when you have your modulus of electricity, you can, if you know your change in temperature, you can know your thermal expansion coefficient, so you can complete your stress. So this is a property of silicon carbide. So the thermal expansion coefficient, this is the unit, and this is the value. So thermal conductivity is watts per mole Kelvin. So thermal shock parameter is in Celsius, and specific heat is in joules per kilogram Kelvin. Applications. So one great example of a thermal property is in temperature sensors. For electronic skin or e-skins can generate electronic signal from external simulation for use as a human-machine interface or HMIS. And multifunctional smart skin. In addition to pressure and strain sensing, achieving the simulations detection and monitoring of temperature with the most efficient fabrication is important. possible means of multifunctional human skin. In stretchable graphene-based multifunctional skin sensor matrix, the matrix can detect and monitor humidity, temperature, and pressure through a sample communication process. So that's all